So here we go. All right, so proportions are used to answer yes/no type of questions for populations. You know, are you a Democrat? Yes or no. Did you vote in the last election? Yes or no. Are you in high school? Yes or no. Are you over 25? Yes or no. That kind of thing. Now, remember that we studied something else that had two outcomes, you know, and maybe that would be binomial. So there's a link between sampling for proportions and binomial random variables. We're going to see that in a little bit, but for right now, let's move on. Okay, since we have a true proportion out there of, say, Democrats in a population as big as the United States, that's something that's just too big for us to try to get to. So we're going to do the same thing that we did with means. We are going to work through sampling or use p-hat values to estimate that true parameter. So parameters p, sampling outcomes are sample proportions, p-hat. You should have this somewhere in your notes previously. All right, so facts about your sampling distribution for p-hat. Sampling distribution of p-hat is close to normal. So if we can verify the normality of the sampling distribution, we can do Z procedures. We can do standard normal calculations. The mean of the sampling distribution of p-hat is the parameter p. So if we could get enough sample proportions and then average them, we should start approaching the true value. So if you know either one, then you know the other. This is what's kind of different. Your sampling distribution standard deviation has its own formula. It's the population proportion times 1 minus that over the sample size. Take the square root and you're good to go. Now keep in mind that you do have some static values, which would be p, and you have a variable value, which is n. N is sample size. It could be small or large. But just think, as n goes up, the whole fraction gets smaller. So you're going to start seeing that same effect as you increase sample size. You're going to have more accurate outcomes, and you're going to get sampling distributions that are taller and skinnier and less variability. So remember, for means, it was sigma divided by radical n. Here it's p times 1 minus p over n, and you take the square root. All right. Again, as n increases, the standard deviation decreases. I think I just said that. So to cut the standard deviation in half, just like with sampling distributions for mean, you have to multiply your sample size times 4. So there's something that should look very familiar. Okay, we've got 2 rules of thumb, and these are going to be things that will enable us to do calculations, normal calculations, that kind of thing. Eventually, these things will become assumptions for inference, and we start inference Thursday of next week. So, rule of thumb number 1, that formula, you know, sigma sub p hat equals the square root of p times 1 minus p over n. That formula is only valid when your population is at least 10 times the sample size. And I think we had something similar for means. So this may seem hard to verify, but we're going to see it's really not that hard. All right. To do a normal approximation, in other words, to do normal calculations, we have to verify. Oh, excuse me, I was overcome with a yawn. That's not good. We're going to have to verify that these two products, n times p and n times 1 minus p, are both at 10 or higher. All right? If one of these is below 10, that kind of indicates a skew. And I believe if both of them are under 10, then your sample size is just not adequate enough. So this needs to be verified before we're able to do any kind of normal calculations. And again, these rules will become assumptions along with, I believe, one or two other ones that we will use in order to proceed with inference and estimation. Okay, so this is the homework. It's in the textbook. So go to your online textbook and go for it. In the meantime, we're really not done. So we're going to move out of your PowerPoint and into that globe activity. So let me go ahead and create a pause here, and I will be right back. All right, so here we go. We're back at, this is in your packet. It is your globe activity. Make sure my pen is there. There it is. And so go ahead and turn to that, and we will proceed. And you'll actually see that some of those PowerPoint ideas in action. What we did was blow up the globe. We flipped it around the room, and people, wherever their index finger on the hand they write with landed, whether it's water or land, we recorded it. And at the end, we had a bunch of hash marks for land and a bunch for water. We counted them up, and we were using 35 tosses, so n is 35, and we just got sample proportions, so it was easy enough. Sorry you had to miss the fun. But so if the world is made up of approximately 70% water, that is a parameter. P is 0.7. All right? We used the globe to give us proportions of water on the globe, and we did 35 tosses to represent one simulation. So we didn't just do it over and over. We did 35, and then we just used the data that we got. So find the mean and standard deviation of the proportion p hat of the water. All right, they're asking us for values for sampling distributions. So mu of p hat, very simply, is the same as the population parameter, so that's 0.7. All right? So then the standard deviation, we do have to check some conditions, but we'll do that in 2 and 3. So sigma of p hat, that's going to be the square root of a fraction, so put a fraction bar there. So 0.7 times 0.3, n is 35. If you do the math in your calculator, you get sigma of p hat is 0.0775, right? And these things do not require any units, so we're ready to go. Number 2, explain why you can use this formula that we did right here for the standard deviation of p hat in this setting, all right? So let's just write out why. We can use the formula for the standard deviation of p hat because well, we tossed the ball 35 times, which set an upper limit on it, but if you think about what the upper limit might be, which would then be the entire population of tosses, well, there isn't one. So we can just say because the population of all tosses is way more than 10 times the sample size. And that would be our rule of thumb number 1. So we met that. So that 0.0775 is quite valid. And then it says check that you can use the normal approximation for the distribution of p hat. That would be rule of thumb number 2. And we're supposed to check these two products. And we'll just see, let me get that off of there. I don't really want that. We're checking to see if the product of n times p is greater than or equal to 10. So that would be, let's see, n is 35 and p is 0.7. That'll give us 24.5. That is bigger then 10. All right. And then we'll check n times 1 minus p. That'll be 35 times 0.3, and that'll give us 10.5. So we just kind of slipped barely under that condition, but we did make it, so we're good to go. So we'll just indicate that so that both exceed 10. So normality of the sampling distribution is approximated. Oops, let me spell that right. All right, remember that your sampling distribution is approximately normal in every case, but as soon as you meet these requirements, it's so close to normal that you're ready to go and do your standard normal calculations. Okay, so it said find the sample proportion. Sadly, you and I cannot toss the ball around, so we're just going to grab one that we did find in class. So let's say that we got 26. So we had 26 successes. And that's where we landed on water, right? So p hat is going to be 26 out of 35, which is, let's see, 0.7429. Okay, all right. And what we're supposed to do is find the probability of getting an outcome this extreme or more extreme, and that would look something like this. This is the probability that p hat is greater than or equal to 0.7429. All right, and so that's the probability. We got to go to z calculations, that z is greater than or equal to 0.7429 minus the mean 0.7 over the standard deviation. It's 0.0775. And let's just go ahead and do this the quick way. So this would be normal CDF. All right, the low end of that would be 0.7429. The upper end of this, well, I think the probability can't, or the proportion can't go over 1. So we'll just do 0.9999, which is really close to 1. And let's see, and then the mean is 0.7. Standard deviation is 0.0775. And that's going to give us 0.2899. All right, so about 29% of the time we would see a sample outcome this large or larger. Now it came up in second period that, well, what if we went the other way with it? We went from negative 0.9999 to 0.7429. They're a little vague in the question, so probably the most easily understood would be to figure out what side of 0.7 you're on. This is the right side, and so we did a right tail calculation. So if we were to draw this out, you know, this would be centered at 0.7, and we'd be looking at 0.7429, and we'd be looking for this. I suppose you could go the other way if you wanted to, but this seems to make more sense. All right, so for number 5, what sample size would be required to reduce your standard deviation of your sample proportion to 1/2 the value you found in 4? That, you have to quadruple your sample size. So 4 times 35 would be 140. And that's really all the problem asks for, but let's just go ahead for grins and calculate that sampling distribution standard deviation with that bigger sample size. So this would be 0.7 times 0.3 over 140, take the square root, and in fact you do get 0.0387, which is 1/2 of what we got up here. All right? So that's basically the globe activity. Now, the next page has a couple of more things, so I'm going to hit pause, and we'll get to that second page. All right, so we're at page 2, and it says, using your calculator, run a simulation to model the number of water events, I should say events, out of 35 tosses. Once you get your sample proportion, find the probability of an outcome as extreme or more extreme than the one you got. Okay. To run this simulation, you got to think about what your situation is. All right, let's think about it. See if it sounds familiar. You either land on water or you don't. Okay. The probability of landing on water is always 0.7. Okay. Every time you toss the ball is independent, and there is a fixed number of trials, 35. Whoops, that's binomial. All right. So we are going to do a random binomial, and it's in your calculator. I'll show you where it is. So random binomial, and so this is going to be 35 attempts. Probability of success is 0.7. And we want to run just one simulation because it says run a simulation. Okay? So here it is in your calculator. You're on your home screen, so it's menu. Okay, let's go. Let's try going into a calculator page. So menu, probability, random, binomial. All right, and let's go ahead and, I don't know why it's behaving this way, stop behaving this way. So it's 35, comma, 0.7, comma, 1, enter. And that's telling us 22 successes. Now, I'm not going to use 22 because my notes have 27, but I mean, we could just keep doing this and eventually we would see 27. Eventually. Oh, there's one. So let's just say that we did this and we got an outcome of 27. All right. That means we got to create a sample proportion p hat, and that's going to equal 27 over 35, and that'll give us 0.7714. All right. So there's our sample outcome. All right. So then we say find the probability of an outcome as extreme or more extreme than the one you got. All right, we can do that. Now I'm going to again do a right tail calculation because, you know, of the way things worked out here. Here's 0.7 and here's 0.7714. So that much or higher. All right, so this is the probability that p hat is greater than or equal to 0.7714. All right, we'll go ahead and standardize. That's the probability that z is greater than or equal to 0.7714 minus 0.7. And it's 35 attempts, so it's still that same standard deviation, 0.0775. And let's just shortcut that. So this will be normal, CDF. The low end will be 0.7714. The high end will be 0.9999. And that's 0.7 for the mean, 0.0775. And so that'll give us 0.1832. So about 18% of the time we would get a sample outcome this high or higher. Or actually this is proportion, so we're really talking about this. But it relates directly to number of successes. So do you see the connection between binomial and just inference basically for proportions? It's closely related. All right, so here's the last thing. And second period people, this I'm going to give you a much better explanation for it. So sorry about how things went. It's somehow I thought I was ready for it and it just didn't work out. So suppose the water covers 70% of the world. What would be the probability that the sample proportion p hat from a simple random sample estimates the true value 0.7 within plus or minus 2 percentage points. And what they're saying here is they really want the probability of your sample outcome being between 0.68, so that would be p hat would be between 0.68 and 0.72. Now we have 3 different sample sizes, the one we've been working with and then 2 others that are bigger. All right. So we'll start out here with n equals 35, and we already know that sigma sub p hat is 0.0775. That's what we've been working on all this time. So, and remember, this is a central calculation. These values are to either side of 0.7, right? So it's kind of the middle part of your curve. So let's do the probability, and I'm going to kind of shortcut this. Let's see, 0.68 minus 0.7 over 0.0775 is less than or equal to z, which is less than or equal to 0.72 minus 0.7 over 0.0775. And we'll just do the quick way of doing this. So normal, CDF, the low end is 0.68, the high end is 0.72, the mean is 0.7, and the spread is 0.0775. And this will give you 0.2036. So about 20% of the time, with a sample of size 35, you would get sample outcomes between 0.68 and 0.72. Okay, so looking at this, if I move on to n is 200, then yeah, my low end stays the 0.68, my high end stays 0.72. The mean is still going to be 0.7, but it will change the standard deviation. So we need a new standard deviation. So let's just make a new line here. So the new sigma of p hat, we'll just recalculate. That'll be 0.7 times 0.3 over 200 now. So this will give us a new standard deviation of 0.0324. So we don't need to repeat a whole lot of stuff. We'll just go ahead and do a normal CDF. And again, it's from 0.68 to 0.72, still 0.7, but now we'll replace our 0.0775 with 0.0324. It gets smaller because the sample size gets bigger. So you've got a taller and skinnier sampling distribution. Now the question is that going to make your probability go up or down from what we had in the first go? And it turns out that it goes up, 0.4630. Now why does it go up? Well, it goes up because this sampling distribution is a lot more broad, right, than this sampling distribution. Since your standard deviation is a lot smaller, this will be a lot taller and a lot skinnier, and it's going to concentrate more of your probability between, like values on either side of the center, and your tails just collapse down sooner than they do up here. So you're capturing, like here you might capture this, but here you're going to capture a lot more of the area. Does that make sense? So let's section that part off, and we'll go to n is 1200. All right, that means yet another standard deviation. So we'll recalculate. So 0.7 times 0.3 over now 1200. Now this should be a lot smaller, right? So 0.01323. So things keep getting smaller, and that will now replace this. And we should see the probability keep climbing, because the same effect will be in play here, but it's just going to be more pronounced with a smaller standard deviation. So now 0.01323. All right, and this does in fact jack up your probability to 0.8694. All right. So there you go. That's what this is supposed to show you. So let's summarize and just say as n, your sample size increases, sigma p hat will decrease, so it decreases. And that means that, let me fix that, we don't need two periods there. Here. That means that the sampling distribution my device is going to restart. Splendid. The sampling distribution gets taller and skinnier. Concentrating more and more probability. In the center and less in the tails. All right, sorry you had to sit through me writing all that, but that's what's going on, all right? And you see this effect when the values are really placed sort of equidistant from the center, right? And so that's where most of the probability is in a normal curve anyway. You just keep concentrating it more and more as the curve gets taller and skinnier once your standard deviations start dropping. So this is what we covered.